Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
So we'll now go to another parameter called tensile strength. That is the tensile strength or ultimate tensile strength (UTS), the maximum load divided by the original cross-sectional area of the specimen, which is also called tensile stress. Is a maximum load. Okay, maximum strength, which is given by SU. S is engineering stress, U is ultimate, which is V max by A naught. And that is about the strength, and we will talk about measure of ductility. What are the measure of ductility? The conventional measures of ductility that are obtained from the tension test are the engineering strain at fracture, that is EF, usually called elongation, and the reduction of area at fracture, that is Q. So elongation and reduction in area are the two measures of ductility in a material that is actually obtained from the simple tensile test. Both of these properties are obtained after fracture by putting the specimen back together and taking measurements of LF and AF. LF is the final length and length after fracture. AF is the area after the fracture. So which is given by the formula is this: EF is equal to LF minus L naught by L naught, which is elongation, and the reduction in area Q is initial area, that is A naught minus AF divided by AF. Both elongation and reduction area are usually expressed as percentages. Because an appreciable fraction of plastic deformation will be concentrated in the neck region of the tension specimen, the value of EF will depend on the gauge length L naught over which the measurement was taken. Very, very important. Just because necking takes place, we will see the importance of necking and what it, how does it determine some of the basic properties, or how does it capture the basic properties of the material. We are going to see it. But we are now looking at the ductility parameters, and considering elongation as a ductility parameter is an issue. Issue is what? Since the plastic deformation will be concentrated in the neck region, the elongation will depend upon the gauge length L naught, okay, over which it is being measured. The smaller the gauge length, the greater will be the contribution to the overall elongation from the neck region, and the higher will be the value of elongation. So there is a bias here, okay, depending upon what gauge length you are choosing. So it is always important. Therefore, when we are reporting values of percentage elongation, the gauge length L naught always should be given. While reporting this without mentioning the gauge length, the percentage elongation will have a biased value. We need to remember this. The reduction in area does not suffer from this difficulty. So you can say that reduction in area is a better measure of ductility than the percentage elongation because of this, the gauge length dependence. Reduction of area values can be converted into an equivalent zero gauge length elongation from the constancy of volume relationship for plastic deformation. That is, AL is equal to A naught L naught. We can play around with these relations from the constancy of volume relationship. So L by L naught is equal to A naught by A, which can be written like this: 1 by 1 minus Q, and then this engineering strain can be written like this. So L minus L naught by L naught, which is equal to A naught by A, which is taken from here, and A naught by A by minus 1 is equal to again this, and this minus 1 is equal to this. This represents the elongation based on a very short gauge length near the fracture. Please, you have to remember. The other fundamental property which can be assessed by simple tensile test is resilience. What is resilience? The ability of a material to absorb energy when deformed elastically and to return it when unloaded is called resilience. This is usually measured by the modulus of resilience, which is the strain energy per unit volume required to stress the material from zero stress to the yield stress sigma naught. The strain energy per unit volume for uniaxial tension is given by U naught is equal to half sigma x times Ex. So stress into strain. Okay. From the above definition, the modulus of resilience is UR can be written like this: half into S naught into E naught, which is equal to half S naught into S naught by E, which is equal to 2V. Okay. So here, what is this? Suddenly S naught is coming. So S naught is nothing but the proof stress. What is proof stress? If the material is not showing any yield point, we take something called a proof stress. We will demonstrate it now. How do we take the proof stress? The proof stress is considered yield stress. So S is engineering stress, S naught is a proof stress. So the toughness. So next parameter is toughness. The toughness of the material is its ability to absorb energy in the plastic range. So we were talking about resilience, which is in an elastic range. So this is particularly a plastic range. The ability to withstand the occasional stresses above the yield stress without fracturing is particularly desirable in parts such as freight car couplings, gears, chains, and crane hooks. So these are all some of the typical applications where the components will be subjected to the occasional stresses which is above the yield stress. One way of looking at toughness is to consider that it is the total area under the stress strain curve. So you see here the typical stress strain plot is shown, one for structural steel and another for high carbon spring steel. You can see both of them, the shaded area shows about resilience, and the total area under this is a toughness. So for ductile metals which have a stress strain curve like that of the structural steel, the area under the curve can be approximated by either of the following equations. So we can use this approximate equations: ut approximate equal to su times ef, or ut is equal to s naught plus su by 2 times ef. For brittle materials, the stress strain curve is sometimes assumed to be a parabola, and the area under the curve is given by ut approximately equal to 2 by 3 su times ef. All these relations are only approximations to the area under the stress strain curves. So these are all very, very preliminary and basic equations, or the property one can derive from a simple tensile test. This is what we are trying to show here. Okay, we are talking about strength. Strength we are relating with yield strength or tensile strength or fracture strength, and we are also talking about ductility, which can be measured by the percentage elongation or reduction in area. We are talking about resilience, we are talking about a toughness, and so on. So now we'll talk about a true stress, true strain curve. So why do we need this in the first place? Okay, what is the definition of a true stress? What is the definition of engineering stress? Engineering stress is load divided by original area of cross section. On the other hand, true stress is load divided by the instantaneous area of cross section. That means the true stress exhibits a complete characteristic of a deformation behavior of a material, right, rather than the engineering stress. So that is how you have to look at it. Okay. So the true stress sigma is expressed in terms of engineering stress from the volume constancy of plastic deformation. One can derive this very simple, but it can be given. The true stress can be given like engineering stress times engineering strain plus 1. The derivation of equation assumes both constants of volume and homogeneous distribution. Excuse me. homogeneous distribution of strain along the gauge length of the tension specimen. So this is very important. So where does this homogeneous distribution takes place in a stress strain curve? Up to maximum load. Only up to maximum load the homogeneous distribution of strain happens. Then up to this point this can be used. So thus the equation should be used until the onset of necking. So once the necking starts taking place, it is no longer a homogeneous distribution. So these relationships will not hold good. Beyond maximum load, the true stress should be determined from actual measurements of load and cross-sectional area. That is sigma is equal to P by A. The true strain epsilon may be determined from the engineering or a conventional strain E by epsilon is equal to ln times E plus 1. So what is shown in this schematic here is engineering stress strain curve together with the true stress strain curve. Okay, the maximum load which is shown is correspondingly it is here in the true stress strain curve. So this is a fracture and this is a maximum load, and you can see that since the true stress is defined by the load divided by the instantaneous area, as the necking takes place, as the diameter, the cross-sectional area keeps on coming down, so that the stress keep on increasing to the fracture. Of course, there is a dotted line, which is suppose if you try to predict this behavior by some of the semi-empirical relations, there is also correction for necking behavior is also suggested. So we will see one by one. What is it? Okay. So these equations is applicable only to the onset of necking for the reasons discussed above. Beyond maximum load, the true strain should be based on the actual area or diameter measurements. So which is given by this epsilon is equal to ln A naught by A, which can be related to this. Finally, it can be measured. What is measured is a diameter, that is epsilon is equal to 2 times ln D naught by D. So what is true stress at maximum load? This is again very simple substitutions, but then we need to know this because all these assumptions are valid up to the maximum load. So you take this expression SU, sigma U, epsilon U with respect to the maximum load only. We can also, rewrite this expression. Rewrite these expressions like this: sigma U is equal to SU times A naught by AU, or EU is equal to S into epsilon to the power, E to the power epsilon U. This is another relation you can derive from this simple equations. True fracture stress again is a load at fracture divided by the cross-sectional area of the fracture. This stress should be corrected for a triaxial state of stress existing in the tensile specimen at fracture. So what we are trying to say is you cannot simply take this value. We have to take care of the other correcting factors like correction for necking, correction for triaxial state of stress, and so on. True fracture stress, again now true fracture strain, which is given by epsilon F. True strain at fracture is equal to ln A naught by AF. This parameter represents the maximum true strain that the material can withstand before the fracture, and it is analogous to the total strain to fracture of engineering stress strain curve. However, for a cylindrical tensile specimens, the reduction of area Q is related to the true fracture strain by the relationship epsilon F is equal to ln 1 by 1 minus Q. So I'm going a little fast because these are all simple substitutions, but you have to know all these parameters so that you will not misinterpret when it comes to interpretation. True uniform strain. Very important parameter. What is that? The true uniform strain epsilon u is the true strain based on the strain up to the maximum load. It may be calculated from either the specimen cross-sectional area AU or the gauge length LU at the maximum load. The uniform strain is often useful in estimating the formability of metals from the results of a tensile tension test. So you please see that by just measuring the uniform strain, we have some idea about its formability. Formability is again important parameters in the metal forming applications. So one can get some idea by measuring this. UU is equal to ln A0 by A. True local necking strain. What is that? The local necking strain epsilon n is the strain required to deform the specimen from maximum load to fracture. So epsilon n is equal to ln AU divided by AF. The flow curve of many metals in the region of uniform plastic deformation can be expressed by a simple power curve relation, also known as Holomon equation, which is equal to sigma is equal to k times epsilon to the power n. So this is quite popular empirical relation known as Holomon equation, which is valid up to maximum load in a stress strain curve. Okay, where n is the strain hardening exponent, k is the strength coefficient. Very widely used. Okay, most popular and very simple equation. So widely used, and it is not just one expression like this for approximating stress strain behavior. There are several of them. So we will see a couple of them, which is most widely used. And in research, people, if you go and look at the literature, there are n number of empirical relations are done to predict the stress strain behavior of a variety of materials. Okay, so we can one can take any empirical relations according to the material with which you are working or looking for information, and then try to estimate all these parameters one by one. Couple of them we will show it in this course. So next thing is what is shown here is how to estimate this strain hardening exponent n. So and the k. So basically it is a log true stress versus true strain. So you get that a straight line, a log of true stress versus true strain. You get a straight line like this, and the slope will give you the n. A by b is n, and this is the k. This is the k. For different, what is the significance of n? If n is equal to 0, the stress strain curve will look like this. So what is the meaning of a stress strain curve appearing like this? It is perfectly plastic. Okay. And what is n is equal to 1? N is equal to 1 is, it's a linear relationship, right? Perfectly elastic. And n is equal to half, it is material undergoes kind of a strain hardening. So something like that. So these are all the this plots gives at least captures the idea of what is the meaning of n, strain hardening exponent. Very important parameter. As I said, by measuring n, you can relate that to formability of metals and strain hardening ability and so on and so forth. We are going to see them one by one. The strain hardening exponent may have values from n is equal to 0, perfectly plastic solid, n is equal to 1, elastic solid. For most metals, n has values between 0.10 and 0.50. It is important to note that the rate of strain hardening d sigma by d epsilon is not identical with the strain hardening exponent. from the definition of n, because we are doing a plot of log of sigma versus logma epsilon, then we find n as a slope. So this can be written like this: a natural ln sigma by natural ln epsilon, which can be written like this: epsilon by sigma times c d sigma by d epsilon. So the d sigma by d epsilon is equal to n times sigma by epsilon. So that is what is written here. The strain hardening rate d sigma by d epsilon is not identical with the strain hardening exponent. So they are very different. This relation we will use it later to use this relation to show that we will be able to get the uniform strain epsilon u can be directly related to n. So n can be related to uniform strain epsilon u. So later we will show that, and this relation we will recall that time. Okay. One common type of deviation is for log-log plot of the above equation, Holomon equation, to result in two straight lines with the different slopes. Sometimes data which do not plot according to the above equation will yield a straight line according to the relationship which is given here. So sometimes the Holomon equation is modified in this fashion, that is sigma is equal to k times epsilon naught plus epsilon to the power n. Another common equation is called the Ludwig equation, which reads like this: sigma is equal to sigma naught plus k epsilon to the power n, where sigma naught is the yield stress and k and n are the same constant as in the Holomon equation. This equation may be more satisfying than the Holomon equation, since the latter implies that at zero true strain the stress is zero. Okay, so it assumes the friction stress at least. So zero true strain, zero true strain, the stress is zero here. So that is what it is. The true strain terms in the above equations, both equations, properly should be the plastic strain actually, which is epsilon p is equal to epsilon total minus epsilon elastic, which is equal to epsilon total minus sigma by e. Okay, so since we are talking about the strain hardening ability, the more appropriate strain is plastic strain. So we have now looked at two models, that is Holomon equation and Ludwig equation. These are the two basic models we looked at it. We will look at some more model which will describe this stress strain behavior. Morrison has shown that sigma naught can be obtained from the intercept of strain hardening portion of the stress strain curve and the elastic modulus line by this relation. Sigma naught is equal to k divided by e to the power n whole to the power 1 minus 1 by n. The true stress true strain curve of metals such as austenitic stainless steel, which deviate markedly from the equation at low strains, can be expressed this type of equation: sigma is equal to k epsilon to the power n plus e to the power k1 e to the power n1 times epsilon, where e to the power k1 is approximately equal to the proportional limit and n1 is the slope of the deviation stress from the equation plotted against epsilon. Still, other expressions for the flow curve has been discussed in the literature. So, like I said, there are like this several expressions are discussed to predict the stress strain curves of metals and materials. Okay, these are I just brought this here just to give you an idea how people try to interpret these results. A convenient model that captures elastic and plastic behavior with gradual transition from the two was proposed by Ramberg and Osgood in 1943 as an aid in the design of aircraft. I brought one important model apart from these two, Ludwig and Holomon. I wanted to present this model because it captures both elastic and plastic behavior together. and this is also quite popular in the mechanics community, very popular model. The basic form of Romberg and Osgood relation reflects the fact that the total true strain is a simple sum of true elastic and plastic strains expressed in terms of true stress as epsilon T is equal to epsilon elastic plus epsilon plastic, which can be written as sigma T, that is true stress divided by E. Don't confuse this with the sigma T. This is sigma T means sigma true stress plus K RO times sigma T by E to the power n RO, where sigma T is true stress, K RO is Romberg Osgood strength coefficient, n RO is Romberg Osgood strain hardening exponent. When the true stress is very low, the elastic strain terms dominates and the behavior is nearly linear elastic. As the stress increases, the plastic strain term plays an increasing role and the slope gradually changes, approaching a regime in which plasticity dominates. So how do we write this equation? It is also possible to introduce an explicit yield strength term sigma y to define a new parameter alpha, which is equal to k times sigma y by e to the power n minus 1, so that the above equation can be expressed as epsilon t is equal to sigma t by e plus alpha times sigma y by e into sigma t by sigma y to the power n rho. So this is understandable when alpha is written like this, and you can write like this, alpha times this one. So this equation is written like this. So what is the benefit? There is no distinct yield point on Romberg-Osgood stress strain curve. So any reasonable value for the yield stress may be chosen, but this choice also determines alpha. When sigma t, that is true stress, is equal to sigma y yield stress, the true plastic strain, that is offset strain at yield, is given by epsilon offset is equal to epsilon times sigma y by e. This makes it possible to select a yield strength value at a chosen strain offset, such as the often used 0.002. I just mentioned in the very first introduction of engineering stress strain curve, there is an offset yield stress that is also called the proof stress. So this is what it is. So the strain axis, you mark this point 0.002 value, and from there you draw a straight line wherever it intersects the curve, that is 0.2% offset yield strength, or it's called proof stress. When evaluated for very large plastic strains, NRO, which is approximately equal to 1 by n. So the values of 2 to 5 or even larger are common. In practice, useful to rewrite the Romberg-Osgood relation so that it more closely resembles the Holomon relation by subtracting the elastic strain from the total strain to leave only the true plastic strain. So we can write it like this: epsilon plastic is equal to epsilon t minus sigma t by e, which is equal to k rho into sigma t by e power n rho, which can be rewritten like this. And finally, you can substitute into this form. Sigma t is equal to e by k rho to the power n rho into epsilon plastic to the power 1 by n rho, which is equal to k, which is equal to h epsilon plastic to the power n. The strain hardening exponent n and the strength coefficient h values can be determined from the more conventional ln epsilon t versus ln epsilon plastic plot. So this is one way of approximating the stress strain curve again. So we will continue this discussion in how to look at this total strain in a stress strain curve, and from there we will move on. So I will stop here now. I will see you in the next class. Thank you.